Welcome back, everybody. Well, last time we got introduced to the world of differential equations, relationships that a function has with its derivatives, maybe its input variable as well. And we saw that one way that we can try and look to get a feel for what a solution curve or solution function to this differential equation looks like is through its direction field. Recall that the idea here is if our differential equation is of this form, y prime equals some stuff, maybe just involving x and y, well then at each point in the plane, we can take that point, that xy, and pop it into this formula, and our differential equation will tell us the slope that our solution would need to have there. And so we can draw it like a little line segment, representing maybe a little chunk of the tangent line at the appropriate slope. And we could do that for this point, and we could do it for this point. Maybe it's supposed to be horizontal over there. Maybe this one's really steep. Maybe down here, this one's negatively sloped, right? We can go through and get these slope values for every single point in the plane and toss on those line segments. And the idea was that a solution to the differential equation is somehow going to pass through that direction field perfectly. And so we could kind of get a visual idea of what these solutions might look like. Today we're going to look at how we can actually start to approximate these solution curves. And the idea is to approximate these solution curves kind of numerically. How can we start to get some values out of this in some coherent way? Well, to start, let's play around with the idea of direction fields and get more of a feel for those. So here I have a grid set up from -2 to 2, just with the integer value points. Let's take a moment and let's sketch onto these points the line segments and get a little picture of the direction field for this differential equation here. Pause the video and take a minute and see what we end up with. All right, so again, the idea here is to take each point, like so, for example, this point right here at 1, 0, and plug it into our formula here. And what we get at that point is 1 plus 0, so y prime would have to be 1, and we could draw a little line segment with that slope there. Right, we can go through each and every point and do that. And one way that I like to set up my work is kind of using a grid where I have just the y's here and the x's here, and then here in the middle, I just follow the formula and add up, in this case, the x plus y. And so right here at 1, 0, this is the slope we just computed over here, and going through, we can get all the rest. And we kind of notice this pattern, perhaps, that along these diagonals, our slopes stay the same. And so our slope's 1 here. It's also going to be 1 along these points on the diagonal. So we'll try and draw all those line segments with those slopes. Slope 2 now for the next 3 points, so a little bit steeper. And then slope 3 for these next 2 near the corner, a little bit steeper, and slope 4 up at the top. Moving on back, we have 0 slope all along this main diagonal. So horizontal line segments here. Then slope -1 below those. Slope -2 next. It's a little bit steeper downward. minus 3, a little bit more steep, and negative 4 down on the bottom left. And so here's the picture that we get for the direction fields of our differential equation here. And so with these direction fields, we can normally not spot exact solutions in the direction field. Normally we can just kind of get a feel for how the solution curves would have to be looking. But sometimes we can actually spot exact solutions if these exact solutions are lines. And so, for example, looking at our direction field here, can you spot a line that passes through this direction field perfectly? And so the way that we could spot that is by looking here at these slope minus ones, right? If we kind of continue in that direction, we're actually going to move perfectly through all those points, and it seems like this line here, what would that be? Y equals, so slope minus 1, so minus 1x, y-intercept is minus 1. So it seems from this picture like that line y equals minus x minus 1 is a solution to our differential equation. It seems to pass through perfectly. Well, how could we actually go through and algebraically check that? How can we check if a function satisfies our differential equation? Yeah, remembering back to last time, all right, this is where we just plug in, right? A differential equation has a left-hand side and a right-hand side. We just need to plug in on both of those sides and see if we get the same thing. Pause the video here and work through that with our function here, and let's see if it actually is a true solution to our differential equation. All right, well, our differential equation, recall, is, let me write it here just for reference, it is y prime equals x plus y, and so the left-hand side is y prime, and so we need to take our function we're thinking about here, take its derivative, and we're just going to get constant minus 1 here, and then the right-hand side, x plus y, we just need to take our y here and pop it in right where we see y in the formula, and doing a little bit of simplifying, our x's cancel out and we're left with just minus 1, and indeed we get the same thing as we did for the left-hand side, and that tells us that this line minus x minus 1, that function, is actually a solution to our differential equation, which is kind of fun. Right? So curvy solutions are much harder to nail down, but we can sometimes spot a straight line solution just from our direction field. But so what about these more curvy solutions? We can kind of feel out what they might look like. How could we get, maybe not what those are exactly, but how could we approximate those in some sensible way? Well, one idea is to kind of get rid of the problem, right? The problem is that these curves are exactly that. They're curving, right? And curves are difficult to kind of get a hold of, but lines are much cleaner. And so one thought is to just imagine that we have a bunch of line segments on hand, and that's what we're going to use to approximate our true solution. And the idea here is we're going to kind of start at a base point, and then we're going to let the direction field tell us what slope to move out from there, and we'll just move up a certain x value each time, and just following the directions from our direction field. And so a quick picture of what that could look like using our direction field, let's imagine here that we are starting right at the origin. And if we imagine that we're right there, well then from our direction field, the slope that we'd want to move out with is slope 0. And so we'd want to move out, say we're moving to the right. Here's where we'd have to choose, how far do we want to step? And just for this first kind of experiment, let's say that we're going to move out 1x each time. That'll be our step size, it's called. So here, if we move out 1 in the x with that slope 0, we would end up right here at this point 1, 0. And now our slope is 1. And so kind of letting that shoot us up from there, we move still 1 more x to the right at that slope, we're going to end up, picture's not quite perfect, but I'll make it bold so it seems reasonable. Right, we're going to end up at this point here, 2, 1. And now our slope is 2, and if we move with that slope and let our x increase 1 to the right, we're going to be shooting up here. I think we'll end up at, what, 3, 3 as our next point, and we could continue the game from there. Right? And that way, we'll start to kind of get these kind of line segments pieced together as a rough approximation to a true solution function. Now, there's an interactive here I want to show us, even though it's quite imperfect. What it's showing here kind of represents the rough idea of Euler's method, which I just realized I haven't introduced that word yet. So Euler's method is the name of this technique of using line segments. So Euler, not Euler, Euler's method. This illustrates the rough idea, but it's actually not exactly right. So what it's showing here doesn't match up, right? From our work before, we should have slope 0 coming off the origin, but this doesn't. So just kind of squint a little bit, right? The idea here is that we're using line segments to get our approximation, and if we kind of move our base point around, we can get some different approximate curves. And the idea is that, well, if we want a better solution, well, let's just step out less and less. So we can make our step size smaller, and as we do that, our line segments get shorter, and as they get real short, right, our approximation starts to look more just like an actual curve. Right? Just visually, it's really not clear that this is made up of a bunch of line segments. It looks just like a curve. All right, but again, if we have real big step size, then our solution's going to be pretty rough. Woo, something like that. All right. And so in order to work this out, it helps to have a formula. And so let's slide down. There's actually a real nice formula for Euler's method. So again, the base point that we're starting at, we call x naught, y naught. And the idea is with each iteration, we're going to move out, a certain amount in the x direction, some step size, we'll call that h. And so to move from xi to xi plus 1, we just take our xi and we add that step size to it. Now the question is, what y do we end up with? And that's going to depend on the slope, right? And so just like we were doing a moment ago, if we're imagining starting here at a particular point, well, from the direction field, we can get the slope that we should have there. So let's imagine that this is a little piece of the direction field. Well, then we would want to move in that direction a certain amount, let x change by that h. And we want to know what y value we're left with here. Well, to start, I claim that we can find nicely this change in y here, this opposite side of this nice right triangle that we have kind of drawn in. The idea here is that this line that we moved along, we know its slope. It's whatever the y prime was back at this original point. We also have another way to find that slope, right? The slope of a line is always rise over run. All right, so this rise over run here has to be y prime, but our run is h. And so rise over h has to equal y prime, and so this rise here is h times y prime. And with that, I claim we get a nice formula, right? So to move from our kind of starting or current y value and get to our next one, well, we just want to take our current y value and add on this rise, right? We need to add on this kind of change in y that we get, h times y prime. And that's really all this formula says. Right, we're going to take our old y. It's a little bit awkward to write this in terms of i's and stuff. I like to think of it like this. So taking our old y value, and we just add on that rise that we see from our picture, the h times the y prime from our first point over here, at least the point that we're bouncing off of to get to our next point. And so a pretty clean formula here. One note about this method is that the errors do build up quickly, and so as much as possible, small step size is useful. We can kind of see that with our first picture that we saw here. Once we do our first step forward, we're already off our true solution curve, and so we're actually going to be grabbing the slope from a point that's not on our true solution curve. And so our approximation can get worse and worse the farther out we go. And so, in terms of implementing this on a computer or something, you'd want to have a really, really small step size so that you're approximating well. Well, let's take our formula here and let's put it to work. Let's use Euler's method with a step size of 0.25 to estimate y of 2 for a solution of this initial value problem. And so let me just take a second here and kind of let's get oriented a little bit with this. So we're looking to approximate the y value for a solution of this initial value problem. So we have this differential equation here. And so we're not going to go through and draw it. We don't need to draw this, but if we wanted to, we could get a whole bunch of points in the plane and start to sketch the direction field for this differential equation. And a solution to this initial value problem is a function that satisfies this differential equation and goes through this point. To have y of 1 equals 3 means that our solution curve has to go through the point 1, 3. And so we're starting here. That's our x naught, y naught, 1, 3. That's our base point. And our true solution curve is going to do its thing, and it's going to have some value. Let me kind of abuse the scale a little bit over the x value 2, right? Maybe it's going to end up here, maybe it's going to end up down here. Euler's method with a step size of 0.25 says, well, we're going to do our little line segment trick and bump up by 0.25 each time. And so here we're actually going to need to move over and iterate 1, 2, 3, 4 times so that we end up at 2 and we'll have some y value that we're left with. And so right away, we can start setting some things up. We know that our base point is 1, 3, and ignore the stuff on the right for now. Don't look at it. We can already set up our x values as 1.25, 1.5, 1.75, and then 2. And that's where we'll be done with our approximating. All right, now to get to from our starting point 1, 3 to our next y value, right? There, our formula uses the old y value and the slope at our old point. And so here we want to find y prime at our base point here, and that just comes through our differential equation, which is right here, y prime equals x squared times 1 minus y. And so here, just taking our x and y, x and plugged it in where x goes in the formula, and our y, plugged that in where y goes in our formula, and just working that out, we see that the slope at our initial point here is -2. And so if we were going to sketch in this direction field, have a slope of -2 there, and so we can see that, well, we're going to be shooting down as we take a step over to the right. But anyways, we don't need to draw a picture at this point. We can just follow the formula. So if we now take our formula here for our new y and plug in the different ingredients, we need our old y, plug in there, and our h we know is set to 0.25, and our old y prime will get plugged in here. We can work that out and get 2.5 as our new y value. And notice that this does match what we were kind of visually seeing before. We took a step down from 3. In this case, we see to 2.5. And now, in order to see what we're going to end up next for our next y value, right, we're going to need to know the slope at this new point, right, our new point being 1.25, 2.5. And so we can take those and plug those into our formula from our differential equation to find y prime. Once we have that, we can then put the pieces together and find a new y value and continue iterating. So at this point, pause the video and see if you can work through this algorithm and get our next 3 y values and see how it goes. All right, so once we get our y prime here, we have the ingredients for finding our new y. We just need to follow our formula from Euler's method. All right, so we just need to take our this is our old y value plus our h times our old y prime. And so now our old y value is this 2.5. That gets plugged in there. There's our h, and our old y prime gets plugged in right there. All right, so we're always just grabbing from the point that we're bouncing off of. And so working that out, we get something like this. And so now with our new x and y values, we can take those, plug them into our differential equation formula, and we get a big long decimal number. As much as possible, we want to, as we're working with our calculator, try not to round those in the middle of our computations. But if you need to, we're not going to worry about it too much. Anyways, I'll just bring up what's coming up next. Once we have that information, we can put that together and find our next y value over 1.75. Once we have our x and y there, we can find our new y prime at that point. And then finally, once we have that, we can feed in to our Euler's method formula to get our y value, y4. And notice this is the y value that's over top of x equals 2. And so this right here, 1.09-ish, that's our approximation for the value of our solution curve, y at x equals 2. There's a nice visual verification we can get for this as well. Another GeoGebra interactive here. So here I have our slope field, our direction field from our differential equation. And I've started us, I think I do over here on the right, I chose our base point 1, 3, and our step size here, they use delta x, it's 0.25, and we can see from the graph, our next step down has us the y value 2.5, then 1.91-ish, 1.4-ish, and then the next one is kind of hidden, but over 2, we're getting 1.09-ish, right? And that's the value that we computed. And so if we continued, it looks like, at least with the rounding they have going on, not much is happening, kind of leveling out. But there's a nice sanity check that our computations are doing what they should be. All right. Well, that's it for today, looking at how we can get numerical approximations to our solution curves just by using good old line segments. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.